right, here we go. Let's take a look at the next section here. We got some correlation going on. Check out this apple core family here, and you can see, you recognize maybe Mr. Sullivan there. It's pretty interesting because his first name is Corey, and they're apple cores. There's his weird brother over here, and a little baby Sully, and then Grandma Sully. Look at this happy family here. Some may say they're correlated. Oh, maybe that could have been a little too hardcore. Let's take a look. What does it mean to be correlated? So that's kind of what we're doing this whole chapter, is looking for a relationship in two different variables. So I pulled this problem off the last packet here. It's a scatter plot showing is there a relationship between if you miss some classes in college, number of missed classes, and your percent for your semester grade. So we want to see, is there relationships there? Is it a strong relationship? Is it a line? Is it a linear relationship? So yes, this one is a linear relationship. I graphed it. You're good to go on this. And what I want to do, this thing is, all last section, I gave you the equation of the best fit line. This time we're actually going to find it. We're going to use a calculator to find that. So you're going to need a calculator on this one. And then we're going to interpret, how good of a relationship is it and what does it mean. So let's just start off to make sure we know what this means. So if I give you this best fit line, I've got this negative correlation here. So it's a pretty good negative correlation. I want you to describe the slope of the line. Well, the slope of the line is negative 9/4. So when I think slope, we think rise over run. And rise over run really sounds like y's over x's. So we've got this y's over our x's. So what does this mean? It's the y value. So you're going to have to label this, and we're going to be very specific here. So I am losing, it's negative, so you lose what? What do you lose? You lose 9, what are these things? Apples, oranges, peaches? Oh, that's your percent grade. You lose 9 percentage points. So you lose 9% semester grade, and that's not good. Lose 9% semester grade every what? Well, this fraction bar here is per or every, so I'm going to say every 4. 4, what are these? Every 4 missed classes. So we're going to spend a lot of time writing this out because it's so important and it's really good. So we're going to use a whole sentence to write this out. You lose 9% semester grade every 4 missed classes. That's what the slope of the line is saying here. Would it freak you out if I made that a decimal? So don't freak out here. If the equation, a lot of times, and especially when we get in the calculator, it's just going to give us the decimal version of this. So this is the same equation. I just took 9/4, made it negative 2.25. So we do the same thing. You are losing what now? You lose 2.25%. But where's the fraction? Well, everything is a fraction. Everything's over 1. So you can say you lose 2.5% of your semester grade. And I hope your handwriting's better than mine. Per or every 1 missed class this time. So make it a fraction. It's just going to be per 1, like this unit right here, every 1 missed class. Awesome. So that's describing slope. Could you describe the y-intercept? The y-intercept is the one without the variable, without the x there. So it's the 85. What does the 85 mean? So that means at 0 missed classes. So this means when x is 0. So at 0 missed classes. So if you make it to every single class that whole semester, you would have what? Your grade, semester grade, I should put semester in there. Your semester grade is an 85%. And then it's downhill from there, according to this model of these students for some certain class here. So according to those students they surveyed and how many classes they missed in their grade, that's what it turned out. So if you miss 0 classes, start with 85%. Awesome. So we're going to spend some time really taking a look at what does it mean. And then now we're going to take a look at how good of a relationship are these things. So we've done a lot of things saying, oh, that's a negative correlation, that's a positive correlation, a strong, medium, moderate, or weak. Now let's really define it with some numbers here. So we're going to take a look at this correlation coefficient. This is also called Pearson's R value. So you're going to see either way, R value or correlation coefficient. This is the formula. Don't write that down. That thing's a monster. That thing's a mess. So this is how you would actually do it. It's kind of looking at like, hey, how far off are these points? That's kind of our whole goal here is if I take a point, how far from the best fit line is it? If I can make this distance really small, it's a better fit. So I'm trying to get really the sum of all these distances to be close to the line. Closer they are, the better fit. So that's kind of the general idea of what's going on. We're not going to do this by hand. Holy cow, let's just even delete it. We're going to use a calculator to find that, and that's more advanced statistics if you want to do that one by hand. So the correlation coefficient is going to be, we say R, and R is always going to equal some number between -1 and 1. So it's sandwiched in there between -1 and 1. So if you are 1, you are a perfect correlation. So come down here, we're going to say if R value is 1, this would be a perfect positive correlation. This would mean your lines are in a absolutely straight line. Ooh, that's pretty good. Absolute straight line like this. That's a perfect positive correlation. So that would be a perfect positive correlation here. So that means your data is a perfect linear fit. So not everything's a straight line, but in this case, if you got a 1, that would be a yes. That is definitely a straight line. Then what happens? Well, we could have something like -1. What's -1 then? Well, it's the same thing, but it's a perfect line and it's in the negative direction. So this would be a perfect negative correlation. It's just going downhill. So kind of like your grade. As you miss classes, your grade gets lower. That would be a perfect negative correlation. So these show the strength and the direction. You got to have both of these. I need both of those. So what happens here then? Well, we have not everything's going to be perfect. So a lot of times we may have something like this where the dots are in the positive. They're correlated positive, and they're not quite 1. So maybe this is around, I don't know, 0.8. This would be a strong correlation here. This would be a nice, strong, positive correlation going through those lines. And as I get more spread out, these dots, and draw them a little bit more spread out here, they get to be a little bit weaker. Maybe that's 0.5. So now all of a sudden I'm at a moderate positive correlation here. So it's still this positive correlation, but the dots are not as linear. They're not as much as a line. So the more it looks like a line, the closer it is to 1. And I put this little graphic up here, and you can see it. I can actually get down to no correlation would be an R value of 0. That just means I've got these random dots. There's no relationship between the two data sets at all. And I can't tell if it's going positive or negative. So that would be R equals 0. Let's just throw another one in here. Maybe R equals -0.2. So if I have something like this, so I've got spread out dots, but they are kind of going in the negative direction here. So this would be a very weak negative correlation. Like this. So the general idea is here, basically if you want to have some guidelines here, if you are anywhere from 0.7 to 1, this is a strong correlation. So we're going to say that's a strong positive correlation. Anything from 0.3 to 0.7 is moderate. Like, yeah, there's a relationship there. It's a moderate positive relationship. And anything from 0 to 0.3 is considered weak. Yeah, maybe you shouldn't use a line here. Not much of a relationship. And the same idea in the negative direction. So make sure you're doing both direction and strength on these. Awesome. Very nice. So there's an R value to tell you how good our relationship is. Now let's practice finding these lines. So what I want to do here, I went ahead and I took this and made a scatter plot. What I need you to do is grab your calculator. Got to have a calculator for this. And I want you to make a scatter plot of this, and then I'm going to show you how to find the best fit line. So just a quick review. To make that, go to Stat. We're going to edit our list, so it's number 1, and go ahead and put your data in there. Mine's in there, but pause it, put your data in there, and go ahead and make the full scatter plot, and then you can unpause. All right, here's my scatter plot right here. Hopefully yours looks like this as well. I went ahead and used the window from the graph given here, so I made that my window. But if you hit Zoom Stat, same thing, you're going to see these points. So these points look like there's a negative correlation here. So our goal is to run a best fit line through there. And when you run a best fit line, what we're going to do is it's called linear regression. So it's the same thing as finding a best fit line. Awesome. So that's called linear regression. So to do it in the calculator, what we're going to do is we're going to come down here to Stat for the statistics. And we're going to go ahead and slide on over to Calculate. And what are we looking for here? We're looking for linear regression, and it's number 4. And you can see it's like this mx plus b idea, except they use a in statistics for their slope. But it's the same idea. A will be our slope now. And when you hit enter on that, we get this little screen, and then we're good to go. We're pulling from L1 and L2. So all you have to do is slide down to Calculate, and it's going to go ahead and calculate this best fit line. Boom, there it is. So what I'm going to do, I'm going to drag it and just kind of have it over here. So when you get this answer right now, this is great. It's going to take it out to 8 decimals. We're going to round things to usually the 100th place. So when I write this equation, and I'm going to put it up here so we can see it, the equation of the best fit line is going to be y equals, a is the slope, so it's in front of the x, so it's negative 1.44. I'm going to round it 2 decimals to that 100th, and that has the x. And then plus the b value, which is 103. Ooh, this is a tricky one to round. 0.997. So that's actually going to round all the way up to what, 104? So we lucked out on this one. It kind of rounds that bad boy up. So 104. So that's great. So what does this mean? We've got this best fit line. So what does it mean if I'm going to try to write the meaning of the slope? My slope is negative 1.44. So what's happening here? I am losing 1.44 what? Losing 1.44. What does this say here? This is my time spent gaming. So I'm losing 1.44 minutes of gaming every what? Per what or every what? It's every what? Every 1 year of age. So as I get older, every year, I lose it's a bummer, 1.4 minutes of gaming, according to this right here. Excellent. So that's kind of what the meaning is going on here. So there's a best fit line, and now I can use this for predictions and all those different things we did. I have that best fit line. I'm going to kind of sketch it in here by hand like this. Whoa, and hopefully your line goes a little straighter. It kind of goes off a little bit there. Can we graph that in the calculator? Because it's nice to have that in the calculator. Sure, let's do it again. I'm going to show you two things right here. First, let's say, if I want to put it in and I want to, you could just go to your y equals and type in that line. The problem is you're going to need to type it out to 8 decimals. To get that most precise answer, it's kind of a bummer to type that out. So if you want to, go for it. If you want a little trick here, when you run your little linear regression, so when you slide over calc and go to number 4, linear regression, it says store regression equation. So you can actually store it into the y1. The hard part is finding where is y1 on this calculator. So y1, you have to go here to variables. As far as is for variables, and you have to slide over to y variables. So we're going to slide over y variables, and we're talking this is a function, and there it is. Finally, there's y1. So if I hit enter here, now I can calculate it, and what it's going to do is not only did it run the linear regression, now when I hit graph, there is the best fit line. And this is cool because now I can start tracing it and using this line to find some values and predictions, use my table and whatnot. So that's a nice little way to go ahead and store your line in there, and then you have it. The other thing we need from this calculator is, hey, how good of a correlation is this? What is that R value? So to run the R value, again, we're gonna get it for you when we do the linear regression. We just have to turn the calculator on. So this is a one-time thing. You have to turn the diagnostics on. So you may have been lucky and you may have already been there. If not, here's how you do it real quick. Down here where it says catalog in blue above the 0, so we're gonna hit second catalog. And now if you notice when you get to here, this little letter over here means that you're in the alpha lock key. So that's good because I don't want to scroll down. There's a ton of things in this catalog. I want to scroll down to what's called the diagnostics. So I'm going to go to alpha D right here above this x to the -1. And that puts me in for the D. So you can see I'm in D. Now I'm going to scroll down. I'm looking for turning my diagnostics on. So scroll down a little bit. And again, maybe you already had yours on. You lucked out. You had a calculator where it's on. Once it's on, it stays on. So all you got to do is do it, hit enter, and now check it out. Let's run that again one more time. Linear regression, slide over calculate, number 4. And now what happens is I'm going to calculate it. And this time when I calculate it, oh, check out this screen. Can you see the difference here? Now I'm good to go here. Excellent. So what happens here, we get a couple different things. It gives you the R values, this very last one right here. So my R value is going to be a negative 0.9, round that to 0. So that's rounded to the 100th place. And what does this mean? This means that we have a nice, strong negative correlation. So there is a strong negative correlation between your age and the amount of time you spend on video games, according to this data. Don't worry about R squared. That's the adjusted R value. We're not going to use that one. We're going to use a plain old R value, and we're good to go. Awesome. Very nice. So let's wrap this up. We got one more problem here, and we're going to take a look at residuals. So we think we're good to go. We got this R value, tells you how good our correlation is, but sometimes it can get a little tricky with that R value. So we got to sometimes take a look at the residual. So what I'd like you to do is go ahead, same thing, go ahead and make a scatter plot of this and see if you can come up with a good viewing window of this or zoom stat this. But go ahead, pause it, type that in, and get us a scatter plot of this data here. All right, here we go. So let's take a look at this. There's my scatter plot. I use zoom stat this time. And if you look at this data right here, here's the data set. Is that a straight line? Well, actually, check it out. It's got a curve to it, doesn't it? So, yeah, we can run best fit lines through any set of data. There may be a terrible correlation, but this is definitely curve, and I want to save that. Let's bring that over here so we can see it. So you're talking about, but I definitely see a curve here, so maybe a line really isn't the best thing for this, but we can actually still run our best fit line through it. So, all right, so let's go ahead and run the best fit line through this. Even though it's curved, we can run a line through anything. Let's go ahead and run a best fit line through there. So here's a quick review. We're going to hit stat, and then remember slide over calculate. And we're going to go to number 4, linear regression. So we're going to do our linear regression, and I'm going to go ahead and store it in y1 because I want to see that line in there. So remember to find that y, it's under variables, slide over to y variables, function, and y1. And I know this seems like a lot, but as you do these, like you do them so much that it's not too bad. And it went ahead and ran it for us, and you can see our R value here. So I'm going to save that. That's a good thing to look at right there. But what I'm really interested in is say, okay, what does it look like when you run a line through a curve? So is that a good best fit line? Well, we've got some points above, we got some points below, but you can definitely see that it's missing a lot. Like it's not really that good. It doesn't show that curve at all. The points above are in the beginning and the end, and the points below are all in the middle. So this is this is rough. This is actually not the best model to choose right now. So I can tell by looking at it here. And the way we can catch this is, check it out. It's tricky. What's the R value? The R value is 0.94. That shows a very strong positive relationship in our data. That says, hey, this is a good best fit line. Like, yes, this is a good linear model. But I can see by the picture it's not. So how we catch this is by looking at what's called the residuals. So the residuals are, it's kind of how they find this R value to begin with. It's how far each data point is from this best fit line. So it's like, hey, how far are these? Well, these are all below, they're all negative. These are all above, they're positive. And then they calculate that R value, and you can kind of see what's going on. So how do we find a residual? This is what you got to know here. A residual is when you take the actual value from your data set and you subtract the predicted value from your model. That's the leftover distance right there. So we're going to do the first one together. So times 0 was 1.6, but if I go to my calculator and I'm going to go to table, so second graph, and I'm going to make sure I'm in this ask mode. So if it says table set, above window says table set, go there, make sure your independent variable says ask and not auto, and then we can ask it whatever we want. So I'm going to ask it, okay, at time 0 or at time 1, time 2, I can type these right in. So according to my model here, 1 should be a negative 13.85. So this predicted value is negative 13.85. Definitely different than the actual value here. And we can get a couple of these. Let's see. We got 3, 4, 5. I think I can put 6 of these. And I'll go ahead and drag these over so I can see them and write them. So my predicted value, if I plug them into the model, I'm going to get something like this. And we're going to round them again to the nearest hundredth. So then it predicts 1.1. That actually rounds up to 1.17, and then 8.67, 16.18, 23.7. So, I got one more, 31.2. So here's the first couple set. I'll do the first couple with you. So if the actual value was this, the model says it's going to be this. There's a big difference there. What's the residual? How far off are you? Well, you got to subtract them. So you just go back to your calculator, if you like, and you say 1.6, and my actual value minus my predicted value. So my predicted value was negative 13.85, and then what is that distance? It's 15.45. Awesome. So let's keep on going here. The next one is 2.7 is my actual value. I'm going to subtract my predicted value, which was negative 6.34. Oops, I forgot the decimal. Kind of important there. So negative 6.34. The distance between these is 9.04. So all that's doing is saying, hey, this distance here is 15.54. This distance here is 9.04. And then we can keep on going. I'm going to do one more with you here. So the next one is 4.4 minus the predicted value of 1.17. And I'm going to get 3.23. So what I'd like you to do is go ahead and pause it and fill in the rest of this whole table. Grab your calculator, fill in those predicted values, fill in those residuals, and then we'll go ahead and make a residual plot, and we will be good to go. All right, here we go. So hopefully your predicted values and residuals look like mine. We went ahead and filled all that, and I know it's a bit tedious here doing all these data points, but we're trying to see, if I wasn't able to look at this graph and I could just look at the residuals, we're going to plot these distance, how far off each point is, to kind of see what's going on. So we're going to keep our x exactly the same. So this is our time in years. And before, y was our subscribers, how many subscribers we had in millions. So this will still be, 0, 1, 2, 3, 4. So let's plug this in. So x stays the same, but now instead of plotting how many subscribers I have, I'm going to plot the residual. So this is my x. The y in this graph was my subscriber. Now my y here is the residual, the distance the data point is off. So check it out. So my biggest residual right here is 20. So maybe, I don't know, can I fit 5, 10, 15, 20, something like this. And then this will be negative 5, negative 10, negative 15, negative 20. So I'm going to plot these points. So 0 has a residual of 15.4, so we're going to just kind of approximate it here. So I've got a dot right there. 1 is around 9.04. 2 is at 3 something. So these are going to be kind of rough, just kind of get a general idea here. Number 3 hits negative. Number 4 is also negative 7.89. Number 5, we're down here. Here we go. So 6 makes negative 11. 7 is negative 10. 8 is negative 8. So, you can kind of see a little pattern going on here. Can you check out what's going on here? 9 is negative 5. 10 is almost on the axis there. and 11 is back up here positive at 7, and 12 is way up here at 20. So when I graph these residuals, this means that this is a bad residual plot. This means that it's not a good linear relationship. That yes, there was a curve here. We should have run some kind of curve, and we're going to do this later on in the year where we actually put a curve through it versus a line. This would have been a good fit curve. The line just is not a good model. You wouldn't get good predictions out of this. So anytime your residual plot has some kind of pattern in it, and you can kind of see the pattern, looks like this little U shape right here, this is bad. If you see a U, this is a bad plot. So even though the correlation said it was a good linear fit, the correlation was actually wrong. You got to take it one step farther and take a look at the residual plot. So here's the main thing I want you to know. That was a lot of stuff. You need to know residuals are the actual value of the data set subtracted from the predicted from your model, and then we use them to make residual plots. Good residual plots are going to be very random, so we want random dots. They'd almost kind of like look like those no correlation graphs where there's no pattern at all going on. So this would be, draw this on there, that would be a very good residual plot. It's random, there is no pattern there at all. So bad residual plots means that no, you should not use the best fit line, that the linear regression is not a good model. They are not random. They're just the opposite. They are not random, and there is some kind of pattern going on here. And for us, for now, we're going to just kind of see this U-shaped pattern. So you may get dots that kind of look like this, and then they come back down. This means, no, this line is not a good fit. You should have used a curve. So it's bad. That is a bad residual plot. Best fit line is not good. If a residual plot looks like this, yes, linear model is a good model, and you're good to go. Awesome. So to wrap things up here, just be careful because we're talking correlation. Here's a great, I love this graph. It says the correlation between global temperature and the number of pirates. So if you look at the y-axis is the temperature, the average world temperature, and this is the number of pirates. So as the number of pirates decreases, the global temperature has gone up over time. So what does that mean? Does that mean global warming is caused by the lack of pirates? Somehow they were keeping the temperatures cool? No, we can't talk about what's causing it. Yeah, there happens to be a correlation, but don't say it causes. So we're going to stay away from anything causing something. Too many variables here. So correlation doesn't mean causation. All right, good luck on the master check. Peace out.